I wanted to talk today about sort of a line of work that I've been doing for a while, and a collection of results that are only loosely related and maybe only related in my head, but they all sort of sprang from the this question somebody asked me, which is, if this will work, how do we compare input cycles or curves, right? So in fact, this picture was suggested to me in grad school by Sariel Harpelid. He said, well, suppose you have different cycles, and he held up his hand and was gesturing to it at the time. How do you detect which ones are more similar? So on this one, is my mouse visible? Can I actually point?
I can see it.
Yay, okay. So the two blue, in comparison to this green one at the bottom here, seem more similar. They're geometrically closer. They're somehow just very similar intrinsically on the surface. But how do we quantify this notion? And how do we assign measures which are then useful in a wide range of application areas? So just my token application areas for those that want to see it. This is coming up increasingly often when you're looking at GIS data analysis, right? Trajectories are often on some planar or nearly planar graph or surface. But map analysis and simplification, computing morphs between curves and parameterizations between surfaces, there's all kinds of, between medical imaging and GIS, you get this type of question quite a bit in a lot of areas. So there's my token applications. Now, where I started from, and the reason this seemed like a good fit for this seminar maybe, was really from the geometry of it, right? People in computational geometry look at a lot of different ways to compare geometric objects. So I started from there, but then, given my own bent and interest, quickly veered into the topology, which was much less explored when I started working on it. So you're getting a bit of a surveying meandering until we get to the actual paper that I'll do the most technical content from. But stop me along the way, because definitions may go quickly, and I tried to include lots of pretty pictures. So whenever geometric people look at this, they say, well, obviously you could just do something similar like Hausdorff distance, right? Take any point on one object or curve or shape, find the closest point on the second, and take the largest of all of them, some kind of bottleneck worst case. If you want the more formal math, there's one version of it. I highly recommend not looking at it, but the idea is, for every point on the blue curve, find its closest point on the red. Now, clearly, this is this red point's closest blue neighbor, right? But if you look at it from the blue point's perspective, well, he'd prefer to go here, right? So this is not symmetric. You do it for both. You look all through the blue and find the closest point. You look all through the red and find the closest, and you take, of all of those, you take the biggest, right? Sort of a bottleneck here. Now, to a topologist, this is an incredibly dissatisfying measure. And even to someone who just does planar stuff, this is like GIS analysis, this is pretty, right? So here I have a blue curve and then a squiggly red curve that goes back and forth. Their Hausdorff distance is tiny, but these two curves don't look similar to each other, right? The person wandering with this way and the person going back and forth are behaving very differently. And so somehow I want to take the underlying flow of the curve into account as well. So in computational geometry, Fréchet distance is usually the next thing you see in a talk like this, right? It's sometimes called the dog leash distance. So you're going to walk along here. I've got the red curve straight. So this is the man walking through the park. And you have a dog that is zigzagging, chasing squirrels around. And the man has a retractable leash. So the question is, if I can consider all the reparameterizations, all the speeds that the man could walk along the red, and all the speeds that blue could walk, what's the minimum leash length that allows the walk to happen, right? So as he walks, you get all these different possible parameterizations, and you take the worst of them. But it's, again, one of these min-max parameters, right? So kind of a bottleneck also. More formally, if you want it, it's the inf overall reparameterizations of how you walk on the curve, and then you take the worst case for that parameterization. So it's an inf because, it's not clear that the min exists nicely, but it turns out in most Euclidean settings it does. It's pretty well studied. So this just to put the first citation, this was probably the most famous initial paper on it, was the Alt-Godot paper, which computed this for two piecewise linear curves in any dimension Euclidean space. I think this algorithm and this construction is actually beautiful. So I'm about to show you a picture that's not mine, because I think their Freespace approach really is worth reflecting on. It's really quite a lovely concept. So this is, you take one of the two curves and you lay it out here on this x-axis. You take the other curve here and you lay it out, or sorry, the x was the longer, the y was the shorter. And for each pair of segments, you say, okay, let's fix a leash length epsilon. Is it reachable, right? For which pieces on this curve and say this one, or in this segment, can the leash stretch? And it might not be the whole thing. So for example, for this much of it, maybe it can reach this whole line, but as soon as you get further away, you can't. And so that's what these Freespace diagram pictures are encoding, is it reachable or not? It's just binary. So it's often shown light and dark. And can I walk with a leash of length epsilon then becomes, is there a way to get through the Freespace staying in the white region, staying in the yes, you can connect it. But I think it's nice because it sort of, and this works in any dimension, right? These could be curves in RD. And all you need to be able to do is take two of the segments and say, okay, if I give you a leash of epsilon, what subsegment of the two line segments can reach each other? And it turns it into this 2D reachability kind of setup, which this is why it's quadratic regardless of dimension, because it's really about matching the two curves to each other and sort of forcing a continuous walk of both people along their respective axes. So anyway, I just like this construction, so I always have to put it in there so everybody can marvel at it and ooh and ah. And we'll get to topology, I promise. I'm moving along. Okay, so Shea distance has been incredibly well studied. I have somewhere 4 slides of citations which aren't particularly relevant for the topology stuff I want to do, so I'll stop with Alt and Godot this time. But what I want to get at is continuous deformation. Okay, remember I'm on a hand in 3D, so let me make that. Let me give you a picture of a surface. Here's a double torus. Clearly, this is a 2 manifold embedded in R3 the way I've drawn it, but I can give this to you as, you know, cellular embeddings and graphs, you know, meshes, however you want to think about this. And if you give me 2 curves, so here I've drawn alpha and beta along here, the question is, can I force it to be continuous? So the reason I don't like Fréchet, as soon as you have not plain old Euclidean space, is it doesn't force the leashes to follow a continuous sweep, right? So let me sketch on this real quick, which I can because we are actually, normally I can't do this. Suppose this had a bump, right? A little mountain in the middle. If you imagine lifting Fréchet distance, you absolutely could just lift Fréchet distance to the surface, but somewhere in the middle, you'd have a leash which sweeps, which it's going to avoid that high curvature length, right? And it's not being forced to sweep continuously, which means at some point, as it stretches around the little bubble, the mountain on my surface, it's going to jump discontinuously to the other side, right? Like infinitesimally further along, it's going to wrap this way behind the bubble, and it's never going to be forced to pay that length, right? So if you imagine, you know, the bottom curve here versus the curve here, you know, as you slide up on a hand, I don't know how well you guys can see where my hand is. Hopefully it's showing up somewhere on the side. You're just going to jump over the fingers because they have intensely high curvature. You get very long when you go over a mountain. And for Shea distance, I could go back, but it doesn't force a continuous sweep of that intermediate area. It just says, okay, well, the best one for this point here and this point here is on this side. So I pay that length. And as soon as I go a little bit further, it's going to be on the other side. Nobody will go over the mountain. So from the motivation of a continuous morphing, which is really where I was starting here, is how do you morph these things in a topological sense? This is not a homotopy. So this motivates the definition of a homotopy, which is a continuous deformation between paths. And I'm going to keep you know, we're really only going to deal with surfaces and really mostly planar surfaces. So we're not going to get too exciting here. But we could, in fact, have curvature here, have holes, have gaps, have obstacles. And so in a sense that even in the plane, you're adding topology to the mix. Okay, let me clear and move on. So homotopy then adds this continuous deformation. Now, it doesn't have to look as nice as I drew in the first picture. So, you know, alpha and beta can intersect and can wiggle and can do all sorts of things. Homotopy's fine with that. It's allowed to unwrap. I've seen this defined as, imagine you have a rubber band and you're allowed to stretch and pull the rubber band, but you can't break it. You're not allowed to lift it off the surface and you're not allowed to break it because it has to do a continuous sweep. I'm guessing most people have seen homotopy along the way, but I kind of like to give the intuition here for those that haven't. Okay, so how do we deal with homotopy? Because this looks more topologically appealing. Now you're imposing something continuous here. So you can certainly test if two curves have been homotopic. I think these are the current best. You can, and these are maybe a little misleading because I should define what M is, or what N is. So you're in the plane minus a set of obstacles. You've got something that's subquadratic to do. Where N is the complexity of the curves and the whole and the obstacles. Now, on a surface, if you're on one of these meshes where it's triangles glued together, there's actually a linear time algorithm, which seems startling until you realize that that linear time encodes the entire surface, right? N is the whole complexity of faces, vertices, and edges. So really, it's the whole complexity of the input. And this is an interesting one. This was first claimed in 1999, and then a bug was found in 2011. And then there's a follow-up paper that simplifies their algorithm quite a bit. Now, this still doesn't really answer if you remember my hand at the beginning with the curves on it, because all three of those curves I drew at the beginning were homotopic, right? The one on the wrist, the one on the finger, and the one further on the finger. The answer is just yes for all of them. There's still no metric attached to this. And so the whole motivation and the whole lead up for this is to try to look at the things like Hausdorff or Fréchet, because they give you a number, right? They really give you a quantification of similarity, and try to lift those to topological settings where we can test homotopy, but it turns out to be much harder to ask the optimization question of what's the best or what's the cost of doing it. Okay. So yes, that's my motivation. These three cycles might all be homotopic, but they don't look very similar. So I want something that comes through and gives these two a lower score and this one a bigger score, right? That quantifies this. All right, I'll pause. I know I go really fast when I get excited. My students always tell me to slow down. Are we still good, or questions? Okay, lots of pictures, nothing else. Okay, so we can, like I said, absolutely just take Fréchet, or there's a notion of geodesic Fréchet where you ask for a geodesic instead of a shortest path, because those aren't unique when you have things like mountains and curvature. Now, it doesn't take homotopy into account. It has exactly that problem I drew earlier, where it can jump over things and not move continuously. So one of the first things we looked at in this line of work was called homotopic Fréchet distance, which is kind of the obvious. Take Fréchet distance, but add the restriction that it must sweep a homotopy. It must morph continuously in the underlying shape that it's living in the underlying space. Intuitively, let me hand wave a little bit. What we thought was that since Fréchet distance turns out to be pretty good in Euclidean space, that this might be a natural way to combine geometry and topology, right? To enforce topological similarity, but then to use the geometry of the underlying space to quantify the similarity. Now, we started in the plane minus obstacles, like good geometers that we are. I can claim that at least a little bit, I hope. So here, what I've got is that same red and blue curve, but I've added 2-point obstacles. So we call this walking your dog in the forest, because there's trees everywhere, and the leash is going to wrap on the trees if the dog runs around it. So you look over all homotopies and you take the longest point. So in this particular relative homotopy class, as the man and the dog walk, the curve unwinds and then it gets taunt around other obstacles and it's forced, right? So by picking the homotopy class, by picking how you wind around the obstacles, you can still sweep continuously, right? So this was homotopic Fréchet distance because we're geometers and we knew about Fréchet distance. And then you just assign the score and look over again, not just all reparameterizations, but also all of these possible ways to wind. So had I instead chosen, let me see if I can annotate again. Had I instead chosen to start in this relative homotopy class, I would have swept, and then I would have started to get caught maybe here. And from then on, I would have wound around somehow with the leash. Okay, now, Annotating is nice, but it requires a few button presses. Okay, so in retrospect, had I hung with more topologists at this point in my career, this is really the width of a homotopy, right? If you think about the curves, and very often when you define a homotopy, this is the continuous, you know, your alpha on one side of it and your beta on the other, and they draw a lot of these squares and map them into things. This is really how wide that square is, where again, these can overlap. Now, I've got the caveat down here that this is incredibly misleading. I'm showing you it on a surface. It's not known how to compute it on a surface. That's one of the big remaining open questions that I hope someone will solve someday. Okay, now what we could do, remember we started in the plane minus obstacles. There's a polynomial time algorithm. Oh, there's a double algorithm. There's a cross that second algorithm out to compute the homotopic Fréchet distance whenever you're given polygonal obstacles. And this draws heavily from prior work with pinned relative homotopy classes in the plane, right, amongst obstacles. This is something a lot of motion planning cares about, is how do you route through things and do shortest paths in the presence of obstacles. So we drew on a lot of that literature to do it. But the algorithm itself is actually quite similar to what Alton Godot did. It relies on the Freespace diagram, but it's more complex because you have to pick how you wind around the obstacles. As soon as you pick a homotopy class, it turns into an Alton Godot style. Okay, well, you have to wind in these way. We know how to do shortest paths in the presence of obstacles and in relative homotopy classes. So I say polynomial and don't pin this down. I'm not sure this is my worst case running time ever, but let's just admit this is a theoretical result. I think it's around end of the 9th or so. I mean, it's considerably harder because we have so many relative homotopy classes that need to be checked. And in each of one, you do an Alton Godot style computation. Now this is older work, 2009. This will, I would like to definitively say, it won't generalize to surfaces. It's heavily relying on the plane being flat. Even in obstacles, there's sort of very limited positive curvature. For all of these, the thing that's going to screw you up is the mountains, right? Anything that takes shortest paths and makes them no longer unique. So any non-positively curved space. The key lemmas just don't work at all. We really were using that this was somehow a planar setup. Now, there, yeah, I had at one point speculated that this might generalize to non-positively curved space if you really want to deal with hyperbolic structures, but I don't know too many people who work on hyperbolic structures. Okay. So the real thing I'll talk the most on is the newer work. So at basically 5 minutes after we came up with the definition of homotopic Fréchet, we said, well, okay, you're measuring width. Why not measure height? Makes total sense. Let's look at it the other way. And in some sense, this is nicer for my original hand image, because what I really wanted to know was how do you slide from one curve to the other? And so, well, the blue curves on the finger, if you remember them, wouldn't have had to slide very much, but the one down on the hand, the bottom of the hand, would have had to stretch over all the fingers and incurred a bigger cost, right? The worst case stretching. So we just did the orthogonal thing, right? And here I can draw on the pretty picture again and say, okay, so you're sliding alpha to beta. What's your longest intermediate curve as you stretch, right? As you slide along, somebody's going to be the biggest thing. Could be alpha or beta, or it could be somewhere in the middle. So just try to minimize that. This is actually also called an L homotopy by Riemannian geometers, which I know less about, although I've started working with some of them. And actually in the combinatorial setting, this turns out to be equivalent to some graph parameters that I'll talk about later. And in particular, there's a paper that studies what they call B northward migrations in graphs. And effectively, they're looking at the same thing. They're saying, how do I walk along the planar thing and start at the bottom and end at the top and stretch as little as possible along the way? What's the best way to proceed? So there's significant work turning this into a combinatorial question, as well as in sort of asking the geometric thing. And I think what I've learned working on this problem is how many connections there are between all the different areas that I didn't expect at the beginning. Okay, so let me lead with the bad news. This came up in 2005. I still don't know if it's computable, period, pretty much ever. I do know that it's an NP. That result was a SOTA paper 2 years ago now, which is what I want to talk about today. But it took, for those interested in working on this, it was a deceptively hard problem. I thought it would be part of my PhD thesis. And it took a lot longer than I thought to publish it. So the next bit I'm talking about really covers 2 papers. So let me cite them at the beginning and thank my co-authors for all the images that they helped provide. So this is all joint work with Arnaud de Mesme and Timo Velders. They were on the SOTA paper, but it's also pulling from a work that's been submitted to the Journal of Discrete Geometry with Greg Chambers and Regina Rotman as well. Greg is no relation, by the way, coincidence, but I do get a double Chambers paper on my CV now. Okay, so what do we do? So let me formalize this, and here we get maybe a bit Riemannian for a minute. So bear with me. If you like graphs and combinatorics, we'll come back to that in a few slides. So I'm going to think of this homotopy as moving through closed curves. So here's the beginning curve, and I can parameterize it. You know, it's S1 cross this. I'm going to call this time, where at each time we get sort of a cycle in the middle. And so figuring out the complexity of this thing precisely turns out to how bad can those intermediate curves be? Can they wiggle around? Can they backtrack? Can they self-intersect? What do they do? Because if I want to compute the best such one, I need to restrict my search space, right? I can't look at every single curve possible in this continuous setting. So I'm going to use h of t for these intermediate curves along the way. So we're going to start with a cycle and we slide it around. Ht gets bigger, gets smaller, self-intersects, whatever, and it ends at the goal end curve here. And then the height, I'll use just the norm for that. And this is in the underlying surface that you're taking it to. Every surface we're looking at today is really just going to be a disk, a plane. I don't want to get to surfaces. Okay, so here we get to some of the topology coming in. The first question when you ask how complex these can be is, can they intersect, right? Can I need to self-intersect? And we started playing with things of, you know, as you're sliding along, would you ever, here, let me just not gesticulate. You know, I can think of even just say you're on the boundary, right? And you're sliding this curve along, somewhere in the middle, maybe you poke it in, and this is another intermediate curve and it cycles around, and then maybe your next one pushes forward more. Would it ever backtrack or self-intersect or do crazy intermediate things like this? Now, when we went to formalize this, the sort of obvious way to think about it is to say, is the intermediate thing actually an isotopy, right? An isotopy is just a homotopy where all of the intermediate curves stay simple. So that's question one. If the thing doesn't stay simple, it's sort of hard to imagine how you could even write a certificate that's not right, that's polynomial time checkable. And remember, we're shooting for in NP. I'm keeping my bar pretty low. All right. So originally, this was in Greg's thesis with his advisor, proved that some optimal homotopy amongst all the possible homotopies, the best one will actually be an isotopy. And the proof is kind of a marvel to me. So bear with me. It starts to look like knot theory and Ridemeister moves, and it's got all kinds of neat connections. So suppose you have a homotopy of height L going from the start curve to the end curve. I'll call those gamma and gamma prime throughout. Well, look at it where the intersections appear, right? So what we're asking is it an isotopy? Will it never self-intersect? So what they do is say, okay, suppose it self-intersects. You start with a simple cycle, you end with a simple cycle. So what are you going to do? Well, you might introduce loops. You might flip yourself. You might introduce bygones if you intersect a different part of the curve, or you might have intersections which flip. And if anybody's seen knot theory, you know, these are the Ridemeister moves. These are very well studied. So what they did was say, okay, take the homotopy and let's decompose it into a sequence of curves where at most one thing happens in between. And so in Riemannian geometry setting, you can do this incurring at most a very small epsilon cost, right? You can say, well, instead of all of these things crossing at once, do them one at a time, and it's sort of an infinitesimal perturbation that they make more formal in their paper. So what do? Well, there's ways to resolve the crossings, right? Remember, my goal is to show you can morph from one curve to the other without intersection. And so what they do in this work is say, all right, think about resolution. So here's my crossings. You know, I've introduced 2 bygones. Some of these yield a simple closed curve, this blue one that I'm pointing at. Some of them do not. Those are red because they're bad, and I like the blue ones, right? I want a consistent sequence of resolutions that's no longer and that stays isotopic. that never introduces intersections. So you can do this, but for each one, but it's not entirely clear that there's a consistent way to do, okay, well, I choose this one. So does that mean that the next one is then possible? And the next, these interrelate to each other. They're not independent. So they then build, they say trivial isotopies of height at most L between good resolutions that are one Ridemeister move apart, right? So for example, this to this, they literally build a graph and say, yep, this is a vertex, that's a vertex, they connect because I can get from one to the other and nobody gets longer. This one is not so clear, right? These two resolutions, well, you're not allowed to introduce crossing, so there's no continuous way to morph this back and connect them. So don't put an edge between these and connect all the good ones that you can resolve consistently. So not all of these will have a trivial isotopy, but some of them do. And then they say, okay, well, they build a graph. Vertices are the resolutions, edges are trivial isotopies of height less than L. And it really boils down to the handshaking lemma, that there's two vertices of odd degree and hence they can find a path. So they take an arbitrary homotopy and from it, they build an isotopy in a really not transparent way because it builds this entire big graph of Ridemeister resolutions that is kind of a nightmare to visualize. But in the end, they're able to prove that one exists. It's not computational, but one of these keeps all the intermediate curves simple, which is good enough for the NNP part that I cared about. Okay, that was a lot of maybe Riemannian Ridemeister stuff, but bear with me. Now, so at this point, the takeaway from this whole section, it's a lovely paper, you can go read it. But what I care about again is now I have an isotopy. I can assume without loss of generality that the best morph, if you start simple and you end simple and you're on a disk, will never introduce intermediate self-intersections, which vastly simplifies the search space because now we have less possible intermediate curves to consider. Okay, now, where we stepped in, determining if you can always find a monotone isotopy. So the other thing for NNP, each intermediate curve stays simple. That's their earlier work. Now, just because each intermediate one stays simple doesn't mean it doesn't back up and intersect between levels. So that's an example over here. This gray one is simple in and of itself, but it intersects a different level set of the homotopy, right? If that's my continuous morph moving inward, the question is, would you ever back up and intersect a prior curve? And this was not in that prior work. This is sort of the next natural question. It's an isotopy, but is it a monotone isotopy? Does it ever zigzag or wiggle back and forth? Okay, now I want to stop and look at this crazy picture if you'll bear with me, because they don't always exist, right? So in particular, suppose we're not starting with the boundary of the disk. Here I've got two curves, one of which winds around these mountains and plateaus here and comes back in the front and is very long. And the question is, what is the best homotopy here? So this is a different version of my hand, maybe. You just got one finger with a curve on it, and this is the one at the base. Okay, now, monotone feels obvious. Why would you ever back up? Well, if you don't back up, here's where I'm delighted that I can sketch. What would this one do? Well, it can't back up. It can't zigzag over itself. So what it's going to have to do is take this segment of the curve, sweep up and over the mountain and get away, and then shrink down this way, you know, level set by level set, and then it can slide up to here, right? So its longest point, if you'll pardon my bad drawing, is somewhere it has to get over the mountain. That's going to be its worst case if I set the geometry as this picture suggests, right? I'm attempting to slide the blue elastic over all the obstacles to get to the little blue one. Okay, now the problem with that, and the reason it can zigzag, is I can do better if instead of coming straight up the mountain here, I say, well, wait on this for a minute, and I come back to this piece of the curve, right? If I instead back it up over the mountain, so that it's like this, behind that little plateau, the smaller mountain, I can certainly set the geometry so that, you know, this is L1 here, and this is L2, and L1 is less than L2. It gets shorter if you pull it over the mountain because it's not wiggling in front, right? Again, I'm hand waving the geometry because it's very intuitive. So now I have a shorter one. If I take this curve that goes behind the mountain, I've gotten smaller, because I already said this piece was longer than the alternative if I slide back over. Now I did have to pay for the little mountain somewhere in the middle. But now I'm back to this sort of local minimum here. And now if I begin to slide this piece over the mountain, I'm going to pay a lower maximum cost. So I slide this down, I'm back here, but I'm still stretched around this. And now I'm going to zigzag back over this one. So here's where you got to like play with it for a minute here. Optimal homotopies can not be monotonic, right? Going back and forth can be necessary. In fact, an open question is how much might you be forced to? I have combinatorial examples, I'll show one later, where in fact you might have to zigzag back and forth log n times in order to get the best homotopy. So it's absolutely not a monotonic action. You might sweep a region twice in order to get a better path and a better length. Let me pause there. That picture is usually takes a minute to process. Everybody's very quiet. No? Okay. All right. So what we do is say, okay, this is bad. When you're not at the boundary of the disk, all bets are off. I don't know what to do. But if you start at the boundary of the disk, this is the work with the bigger group, we show that monotone isotopies always exist if I consider only intermediate ones that sweep the annulus bounded by the input. So here's my here's my outer curve, and my inner curve is here, and I want to slide the outer one down to the inner one through things like the purple curve, right? So, okay, how do you show it's monotone? Well, assume it's not and get a contradiction. Again, this is a non-constructive thing here. So suppose we decompose it into monotone pieces, and we were really inspired by that Ridemeister move, you know, look at one thing at a time. So this is what we're going to do. We're going to look at a monotone sweep, and then at some point it decides to turn around and back up. And then it goes in again, and then it goes back. So that's my zigzag, right? In the intermediate, we're monotone, then we back up, then we're monotone, then we're back up, then we're monotone. And these are going to overlap somehow. So what I'm showing here is just the first piece of the zigzag that you shrink from this outer one to the inner purple one. And again, there can be geometry here. I could be hiding some mountains and hills. I just can't be hiding any topology. There's no handles in here. It's a disk. It's an annulus. Okay. So then here's my next piece. So this was the first one, the shaded light purple over here. And here I've gone from this one, gamma 1, out to gamma 2. Now, of course, these might overlap each other. This is the point, is these could cross and get messier. I'm showing you a very, very simple in and out. So here's the high level sketch, and I'll refer you to the 10 pages of details in the paper, because it turns out to be nasty case analysis. So consider one of these. Here's a prior swept portion, and here's a later curve. I don't know why you did this. It turns out you wouldn't want to do this, but this red curve is a later, you know, I swept from the outer curve here in to the inner one, and sometime later I've decided to sweep backwards out again, right? And it could get really messy and complicated is the problem. This is not just a simple single crossing, because this is a continuous deformation. It can do all kinds of wacky things in here. Okay, so what the heck do you do? Well, we need to break this down and show that we can simplify it. And there's sort of an obvious one suggested by the picture, which is of course a bit of an oversimplification, which is, okay, consider all the pieces that went where I didn't want them to, right? The blue is my previously swept portion, and this later red curve has violated my previously swept portion. Well, I want to show that you don't have to do that. So this is what we do. We break it down into a bunch of cases depending on how it's crossing and say, well, instead of this red, don't do the red, right? Snap the red out of the blue region and instead go on the boundary there so that you never leave your previously swept portion. Okay, does it work? Yes, we construct a retract. Now we have to be a little bit careful. These blue curves where I'm stopping, we have to assume that they are sort of minimal in their possible area. And so there's a lot of technicalities and cases here of how the intersection pattern happens and where you pause along the way. But the intuitive idea is quite natural, right? Well, if this is as short as possible and you chose to go back outside of it, you made a mistake. Stop on the boundary, perturb it so it's not crossing, and just sort of stay in a little infinitesimal region, and you'll be shorter. And that does work with a whole lot of case analysis and checking. Okay, so that's the continuous setting, and I want to move to the discrete setting. I promised I'd get to some combinatorics here too, because I really want triangulated surfaces. But from here, what I'm going to say from this continuous portion is that we can assume without loss of generality that this best homotopy height will always be an isotopy and will always be monotonic, right? That's what this proof did. This proof says, well, if you give me one that backs up, I'll give you a better one that doesn't have to. And again, it wound up being a fairly detailed set of cases. This was a fun one where this was actually part of Greg's thesis. And when we went to try to discretize it, we found a bug in his thesis. And hence the later paper was born with all of us on it because we figured out how to patch it. So when we picked this up, we were more interested in discretizing, right? I at heart like combinatorics and graphs. So in the discretized setting, I'm going to say, well, we have a triangulated annulus. And how do you discretize a homotopy? Here's where it starts to look like graph parameters a little bit more. You might choose to spike, right? You can make a curve instead of using these two edges. If there's a third one there, I can instead make a curve which is topologically simple. This is not graph theory simple, but this is sort of perturbable to a simple path if you think of it as living on it doesn't have to have a crossing. Or you can imagine, here's some piece of the curve. You can flip across a face or flip across a face in its entirety. So any of these are considered discretized homotopies and are pretty well studied. This is actually where the B northward migration work comes in. They didn't consider spikes. They only really considered face flips, but they were interested in pushing a curve across a triangulated planar graph, right? How do you move across a graph so that the longest intermediate is as short as possible, which is the same as homotopy height. Okay. Are the combinatorial moves clear? Because this is kind of a big shift from the continuous world where we're shifting around. Now it turns out these are connected, because if I imagine the underlying surface here, certainly I could take a combinatorial set of moves and build a homotopy out of them. But it turns out with a little bit of care, you can almost go the other way as well. Given a continuous curve, you can discretize it without incurring very much cost. You just have to be a little careful about the accounting along the way. Yeah, so the problem in this setting becomes, well, we're sweeping from the outside of the annulus to the inside via these flips. And how long does the intermediate curve get? We've also looked at it. There's a lot of variance with some very subtle differences. You can also often think of this. I used to draw the picture a little bit differently, if I can annotate, where I would say, okay, imagine you're given the boundary of a disk with gamma 1 and gamma 2, and the goal is to sweep, right? Move across intermediate face flips or edge spikes and end up at the other curve. This is actually the version of it I started with, was going from one side to the other. So that's more like this in a triangulated version. But the annulus one is closer to the Riemannian work. Okay. So like I said, most of the papers have, oh yeah, okay, there's some subtle variations here of whether you mean the outer boundary to the inner or whether you mean one side to the other. But the techniques are very similar, whatever setting you're in. It turns out if you want to go from one side of the boundary to the other, like here, well, that's almost the same as contracting the boundary to nothing along intermediate curves. Some subtleties, but it's very similar. Now, here's where things get messy. And here's the example I promised that we still can't assume the sweep is monotone if we don't begin at the boundary. And in fact, it's easier to get pathological examples. So bear with me here. This is a planar graph. It's not triangulated, but I could introduce some vertices if you want and triangulate it. It's just a bunch of bigons nested. And we're going to start with this length 10 cycle. I really don't want red. Let me go with green. We're going to start with this cycle here that's in bold, right? And it has length 10, 5 plus 5, the way I've started it. So it's allowed to sweep across any face. There's not really spike moves here with the bigons. I've sort of simplified it down to just doing face flips. Well, if I go out, I get bigger. But so if I go in here, I get to 6, and then I can get down to 4. Sure. So at that point, I've gone up to, from 10, I went up to 11 and then down to 9, right? Now, I really want my goal to be 11. The question is, can you do it not getting longer than 11? And at this point, here is my intermediate curve. I'm on this 4 edge. I'm stuck because 8 is big, 6 is where I came from, 7 is big. So I can't sweep in. But if I go out and then to here, I get shorter again, right? So this zigzag is set up precisely to be a zigzag. You can slide in, which gives you some flexibility, so you can slide in, but then you've got to go out to get to the smaller one, which lets you get out, which lets you get in. And in order to get this down and maintain worst case equal to 11, you're forced to go back and forth. There is no monotone contraction of this thing. It's going to go in and then out and back and forth. So I clearly have missed the chat, which I just noticed. I'm going to try not to look at that. It's a bit distracting. So you can sit with this one if you want to. It's actually a fun example to play with. I think this one has log n, if n is the complexity of the edges, that it actually has to go back and forth. But I haven't worked out in full generality. This is actually my co-author Arnaud's example. So now what we can prove, and what the soda paper starts by proving, is that if you're not in the interior, you don't zigzag. That if you start at the boundary of the disk, if I had started at 1 + 1, in fact, there is a way to just go in without backtracking. Somehow the starting not at the boundary is what forces you to have to move back and forth in a way that it's not clear I really fully understand still. So still work to do as how bad this zigzagging can be. But we can, it turns out, discretize the rest of the proof. And so if you start at the boundary of the disk, it'll still be an isotopy and it'll still be monotone, which gives us some hope to prove its complexity. At this point, by the way, this paper and this work appeared maybe 12 years after I'd started working on the problem. So there's some decided subtleties buried in here. Okay, so how do we show that it's actually an NP? Monotonicity will immediately imply that the face flips happen at most once, but it doesn't tell me anything about the edge spikes, right? You can't back over a face. I can prove that, but edges can be spiked without crossing, right? I can spike once this way, and then maybe the curve does something else and winds up coming back, and I can spike across the edge again and not actually cross, right? Just sort of live alongside, and you can perturb it to be simple and it's not a crossing. So we still had a bit of work to do to deal with edge spikes. So here's where we start to get more combinatorial tools. We started by thinking of this in terms of the dual graph. So the annulus is still shown here in my tan with triangles in gray, but now I'm showing a dual graph in blue, right? This is just classic planar dual graphs. We're adding a vertex for each face and connecting faces that share adjacent ones. So monotonicity across a face is essentially the same as sort of grabbing a new vertex, right? If you want to get a new face flip in, well, the dual curve is going to surround the face flip. So you start to get some nice connections with the dual graph and what's happening because we're in a planar graph, so we can consider that. But the issue is that, you know, as if you're spiking across an edge, you could come back and spike across the edge again and not really have a crossing. So we still have something to do here. So what do? Well, we start looking at cases, and here we get the other, this is again a 5-page proof in the thing to do the case analysis. But we're spiking, and if you're spiking back over the edge, you know it's not a real crossing because this would perturb in the Riemannian setting to be simple, right? So the only reason you're spiking is to do another face. And if you're going to spike again, you'd better have another face accounted for. Because if you don't surround faces, then you get shorter by just removing the spikes. So then we get the case analysis of how many times can you spike. In the end, we wind up getting a ridiculous bound, which is not the best possible, I guarantee, that you can't spike more than a quadratic number of times. I suspect the answer should be linear, because each time you spike, it should be a face. But quadratic was good enough for the NP part, so we didn't dither too much about how to get it down faster. But essentially what we're showing you here is the case analysis of, well, suppose you spike, and this is what the rest of the curve does, not near me. Well, how can I simplify and remove one of the spikes and have an equivalent curve? And how can I simplify and how can I simplify? So a decent portion of this paper is this case analysis of here are the possibilities. Okay, so that's most of the soda result. Now, the kind of interesting thing is it turns out homotopy height is really connected to that original homotopic Fréchet distance that I talked about, where instead of morphing from one curve to the other, you've got leashes from one curve to the other. So we couldn't show the normal, so normal homotopic Fréchet, remember, was you've got a P and you've got a Q and you want to walk. Here's a leash and here's a leash, and we're going to morph in between, connecting them with leashes that are as short as possible, right? So this green area in homotopic Fréchet, and there's my annotate tool, needs to be swept by, intermediate curves along the way, right? So this is not homotopy height, because homotopy height is about shrinking the entire thing down. But it turns out a pretty trivial connection gets it there. So if you just add a vertex and connect everything along the top path and everything along the bottom path, kind of cone it off to that vertex, well, now if I want to walk along like this, that's the same as walking inside an annulus and shrinking from an outer boundary over here to the inner boundary over here. Right, so you can actually reduce the homotopic Fréchet to a sort of a variant of homotopy height. These are surprisingly connected, and there's a nice approximation algorithm that came out a few years before our work that exploits this connection to show approximation, a log n approximation for both of them, but not an exact algorithm. We still don't know that. Okay, let me clear here. Okay, so one of the things we've been playing with since then is a recent paper we published in graph drawing last year. It's 2020, so it feels like it's been a lot longer, which points out that in fact this homotopy height parameter is really connected to a lot of graph drawing or cut width type NP hard parameters. And so I'll mention a few of these sort of to conclude the talk, because I think this is interesting. This problem appears to connect to many things in graph theory. I have no idea still if it's polynomial time or NP hard, because it seems to be right on the boundary since it's in a planar graph. So we already talked about dual graphs, clearly everybody's seen those. This is more for when I talk to other audiences. I'm going to assume most people know dual graphs here. So if I go back to my annulus and I dualize, now here's that blue picture again. This is what I alluded to earlier. Face moves from the homotopy correspond to, well, I'm choosing to cross differently in the dual graph, right? A particular curve, well, the red one crosses this sequence of blue edges. And if I flip across a face here, that's saying, well, okay, instead of crossing this dual edge, I'm going to decide to cross these two. And then instead of crossing these two, I'm going to flip here and I'm going to cross these two. So flipping across a face in the primal corresponds to changing intersections in the dual. Pretty standard if you're used to, shortest paths or flows on planar graphs. Now, the weird thing is that edge flips still break this down, because if I choose to spike, I'm adding two edge crossings by spiking in, but in a different way than we would normally think about in the dual graph here. It's not really crossing necessarily, right? This is introducing a spur, which is trivial, which can be gotten rid of and only gotten shorter. Okay, clear. Okay, so when we are looking at this, we immediately land on cut width, right? Cut width is a very similar, the cut width of a graph is, okay, given a graph, give me a linear arrangement of vertices and minimize the maximum number of edges crossed at any time. So I should have a picture here of it. Yes, here, let me just draw quickly. So you're gonna lay out vertices. And of course, if I give a linear layout, there's things connecting them between. Who knows what it looks like? It could have a bunch. And I want over all the possible linear arrangements to minimize the maximum vertical in between, right? So essentially, I'm choosing which edges to intersect by rearranging my linear layout. Now, the only reason this starts to look really similar is that dual connection, right? The dual homotopies turn out to be very similar to cut width. So here's a homotopy. Sorry, here's a planar graph, this gray thing underneath, and I'm showing the dual graph here along with weights. And you can imagine, you know, the 20 is the dual edge can grab the weight of its dual. Weight the same thing because that's what we're interested in minimizing. Well, if I make a linear layout over here of the vertices, you know, I get a weight, right? This length 24 crosses green, green, orange, pink, and purple. So that would be green, green, there's an orange, a purple, and a pink. It turns into a cycle over here, essentially. Precisely the set of edges you cross give you the edges over here, and hence ties back to a homotopy, a set of combinatorial operations. Again, this gets back to that where we were looking at it in planar graphs. Now, cut width of graph is a bit different. So cut width is NP hard of an arbitrary graph. But if you dig into the reduction, and it takes some work to find the paper because it's not a newer paper, it doesn't keep the embedding fixed, right? It relays it out any which way. And for the homotopy height, if I go back a slide or two here, my layout is very much fixed. I'm giving you a rotation system, right? I'm literally saying this is a planar graph and I'm giving you all the faces. This is not the same as a different planar embedding, right? Because I'm fixing the topology in a sense, the underlying surface here. The cut width reduction falls apart for our problem because it doesn't respect the rotation system. It doesn't keep the embedding fixed. It lays it out an arbitrary way in the reduction. So our problem is not NP hard, even though cut width is. We're sort of looking at a specialized instance of cut width. Not quite the same thing. I had hoped for a while we had an NP hardness proof, but it all fell apart. So this is open even with unit weights. And it's kind of a fun one to play with here is cut width for unit weights where I'm keeping the embedding of the graph fixed. It also connects to bar visibility representations, which are kind of a thing you see in graph drawing, where we have each vertex getting marked. So like vertex A maps to line A, vertex B to line B, and any two things that are visible in the bar representation get an edge between them in the graph. A commonly used combinatorial framework for graphs. So if we require bars to be on horizontal integer lines, then sort of bar visibility height is height, right? It's the smallest height. Bar visibility representations, any planar graph will have a bar visibility representation. So again, kind of a connection here that these are the same thing. And bar visibility height is always connected to sort of straight line graph drawing height, right? How do you connect vertices without crossings? So this comes up in the graph drawing community a lot. This is pulling from that graph drawing paper. This particular picture is taken from a co-author of mine, Freespace, 2014 paper. So why are we connected? Well, if we fix an outer face, if we fix a top and a bottom, the bar visibility is in fact a homotopy, right? You can think of this as, well, what do we have? Where did it go? Shoot, there we go. Right, we have S up, or sorry, T is at the top, S is down here. This edge becomes an edge over here. What is this? Well, this is a new vertex appearing in the middle, which T is connected to and which S is connected to. So this introduction is essentially over here is equivalent to a face flip, moving along the bar visibility graph. And we get another one down here and we connect. We get another one here and we start to get, that one's connected. Anyway, here's where my picture breaks down and I should pre-draw it ahead of time. I like to do this one as I go. Yeah, we get another one in here, I think, and connect it like that. So you're sliding from one side of the plane to the other. And if you want the shortest height over in the bar visibility graph, that corresponds to short intermediate curves in a combinatorial homotopy. Which was kind of surprising to me. I didn't see how this had anything to do with graph drawing. But somehow the height of how you draw it really does connect to the homotopy and the way you morph across it. So, is there a planar graph straight line drawing of height H is something graph drawers study a lot. We connect this to a variant of homotopy height with only face moves. You don't have spikes or repeated edges. So again, it's a slight variant of the problem, but it's a similar one. Okay, I think I'm going to skip grid major height. You can read the paper for details on that. And we do other variants in here where we're sort of connecting them to a bunch of different graph drawing parameters. I realize I'm wrapping up on time. And then the last one we connect to is sort of node searching or sweeping, which again, surprisingly turns out to be somewhat connected. But I assume I should stop and allow for questions, or what do organizers prefer?
If you like to speak for a couple more minutes, that would be fine, or?
Okay, well, I can talk about, yeah, so the last one, the one that I've been playing with more often, actually hints at other topological parameters. So maybe this is a good one to end with if you'll give me 2 minutes to explain it. If you've never seen searching or sweeping, there's a bunch of different variants of it, but the idea is you've got guards moving through the vertices of a graph, and somewhere in there, you know, cops and robbers, sometimes you're trying to clean things out and corral and make sure that there's no contaminated things left. So the search number is where at each step you add a new guard to any vertex, you remove a guard or you move along an edge. And an edge is cleared when you move over it. You want to clear the whole graph with as few guards as possible. Connected search number is the same, but you have to keep the set of cleared edges connected. And then it turns out the monotonic search number, if the set of cleared edges grows at each stage, then it's monotonic. So this is pretty well studied in a lot of different variants. Homotopies, in fact, are a type of searching, right? If you think about moving along, if I place a guard at each piece of the curve, I'm sweeping as I go, right? This is why we originally looked at it. Node searching, it turns out, is monotonic. And what I was trying to do was show that homotopy height was monotonic, but it's a slight variant. Now, homotopy height is a bit stronger, though, because it's not that one side has to stay connected. It's that both sides, it's a homotopy, right? It can't break things up. It's got to sweep continuously. So both sides of the cut have to stay connected. Now, it's interesting because connected search number is not monotonic. And here's a picture from their proof. It's fairly convoluted, but it's not mine. So the surprising thing is that even though it's so connected, this is an example that shows that it's not monotonic, even though our parameter is not monotonic. Homotopy height is a monotonic. That's what the isotopy proof proved. So it turns out what this starts to connect to is homology height, right? Where not just continuous sweeps, but if you've never seen Z2 homology, it's allowing collections of curves, cuts in a formal sense. So in fact, in this setting, it turns out to be Z2 homology. We say two even subgraphs are Z2 homologous if their union forms a cut, right? So these two curves are Z2 homologous because their union divides the surface. So it turns out the searching and sweeping numbers are more connected to homology than homotopy, which I think is kind of a fascinating, unexpected thing here. Here's lots of pictures of Z2 homology. So homology length is precisely the same as cut width. So the minimum height homology, call it length here because height doesn't really make sense anymore, actually is the same as cut width. It's NP hard, which I hadn't realized before this. So this is back to this cut width representation that I talked about earlier. So I was surprised because I entered into this expecting homotopy to connect to some graph stuff, but homology came out of nowhere when I started to look at this reduction and think about what it was doing. Okay, so I'll stop here. There's a lot of variants that we haven't even gotten to area. Maybe that's another talk. The biggest open question is I still don't know the exact complexity. Most of the interesting variants are in NP. And that's all I can prove. So I still don't know if there's a polynomial time algorithm or if it's NP hard. And I would say at last survey amongst co-authors that have worked on this with me, we're about 50-50 on which we think it is. We genuinely have no idea. I go back and forth.